Welcome to the second lecture of linear algebra course, linear algebra for AI and ML. In the last class, we had introduced the vectors, and we had studied two different and important operations for the vectors. One was vector addition, and the second one was scalar multiplication. So these were the two operations that we had looked at in the previous class. So what we want to do is we want to recall the properties that we had listed down for this vector addition and scalar multiplication, and we want to define an object. The object is called as vector space. So the object that we want to define is vector space. So basically it is collection of vectors which satisfy certain properties. So that's what we really want to do. So I'll write down the definition and then we will go word by word and we'll understand what we really mean by vector space. So let V be a set and so let V be a set. This set is called, V is called a vector space, over set of real numbers over R if the following properties are satisfied. Following properties are satisfied. So what are the properties? The properties that are to be satisfied are the following. So first define an operation. Define an operation called addition. For so this operation we want to define on V and define another operation scalar multiplication on R cross V. Okay, so this will take addition. So you take two vectors, so V cross V goes to V and the operation R cross V goes to V. That's the operation we want to define. And the properties that need to be satisfied for addition and scalar multiplication. So what are the properties that need to be satisfied? Let's list down the properties. So the first property is addition should be commutative. So for every V1, V2 in V, you should have V1 plus V2 is equal to V2 plus V1. That is called as commutativity. The second operation is associativity. For every V1, V2, V3 in V, what you should have V1 plus V2 plus V3 is same as V1 plus V2 plus V3. So the order of addition doesn't matter. You can add in any order. That is called as associativity. The third property is existence of additive identity. So there exists a zero vector in V such that V plus 0 is equal to 0 plus V is equal to V for every element V in V. And the last thing is existence of additive inverse. So there exists a V in V, W in V for every V in V such that what happens? W plus V is equal to V plus W is equal to 0. So these are the properties for addition. And what are the properties of scalar multiplication? For every alpha and beta in R and V in V, alpha into beta V is same as alpha beta into V. The second property is for 1 belonging to R, 1 V is equal to V for every V in V. The third property is alpha plus beta into V is alpha V plus beta V. And the fourth property is alpha into V1 plus V2 is equal to alpha V1 plus alpha V2 for every V1, V2 belonging to V1, V2. Okay, so these are the properties. So what does this vector space object demands? So basically at this point I should tell you that in mathematics typically there are abstractions that are done. The reason the abstractions are done is because you can collect similar examples together under an abstract object and study that object, so that whatever theorems, whatever properties you can prove for that object, as particular cases will follow for those examples of interest simultaneously. So you don't have to individually look at those examples, you just look at the object, prove certain property for object, as a particular case understand that property for the particular example of your interest. So the abstraction is very important in this sense, and vector space is abstraction of concept of vectors and properties of vector addition and scalar multiplication that we have seen earlier. So if you do this abstraction, that not only the vectors that we looked at in our first class, but many other vectors or many other things in mathematics which have similar properties like the vectors and vector addition and scalar multiplication can be studied under the same umbrella of vector spaces. Okay, so what is a vector space? So vector space is actually a set, and the set has two operations. So one operation is addition operation. So you take any two vectors from the you take any two objects from the set, then define that operation addition. The addition operation should be closed, that means that the sum should also belong to V, and you define another operation called scalar multiplication, the same logic. And you just don't stop at defining, you demand that these operations have certain properties. What are the properties? The properties are these 8 properties that we have listed here. So if all these properties are satisfied, then we say that the vector V is a vector space over R. Why we say it's a vector space over R? Because the scalars are coming from R. So you see here at every statement I am saying that the scalars are coming from R. So these scalars alpha, so these are coming from R. So if they are coming from some other set, the set of complex numbers, or there are certain type of fields which are finite fields which have applications in coding theory and all. So if the numbers, the scalars with which we multiply are coming from different set, then it will be a vector space over that particular set. Okay, so in this particular course we will not go beyond real numbers. So I have defined a vector space over R, the set of real numbers. And what are the examples of vector spaces? The examples of vector spaces, the first one is R2, R3, in general Rn, for any n natural number. So these sets are all vector spaces over R. And why are they vector spaces? Because we already have seen in the last lecture how to define vector addition, how to define scalar multiplication, and we already have listed the properties of addition and scalar multiplication, which are nothing but the axioms in the definition of a vector space. So this is an example of vector space. What are other examples of vector spaces? The other examples of vector spaces, some interesting examples of vector spaces we'll see. So for example, you consider the set S to be the set of all infinite sequences, x1, x2, x3, so on and so forth. xi is in R for each I belonging to a natural. So what are the typical elements of this set? So x belonging to S means that x is a sequence. So for example, I can look at the sequence 1 half, 1/3, 1/4, and so on and so forth. So this is one sequence. I can look at another sequence which is just all ones. I can look at the 0 sequence, which is nothing but 0, 0, 0, 0, 0 all the time. And then how do I define addition and scalar multiplication? The addition and scalar multiplication is defined in exactly the same way as we defined for the vectors. So for x and y, belonging to the sequence S, x plus y is basically the sequence x1 plus y1, x2 plus y2, so on so forth, the infinite sequence. This we will see whether can act as zero vector. So it will definitely act as a zero vector under the definition of sum that we have put there. And for alpha belonging to R and x belonging to S, alpha x is alpha times x1, alpha times x2, so on so forth. So this alpha x operation, so this also is a sequence, and if you verify all the properties that we listed here, then all those properties are satisfied, and then this S is a vector space. Then claim, what is the claim? Claim is that S is a vector space over R. Is a vector space over R. So this is really very interesting that this is a vector space over R. One more non-trivial example of vector space I'll consider, and then we will go back to some interesting examples. So this example is the example, so this is a little bit of mathematical example, but we can nevertheless look at this example. So I will define by f the set of all functions from R to R such that f is continuous on R. So I collect all the functions f from R to R such that f is continuous. So for example, this function f of x defined as this particular function. Okay, so let me draw it with a different color. So f of x defined in this particular way, it's 0 for x less than 0 and is equal to 1 for x. So this function, how is it defined? This function is defined as fx is equal to x for x greater equal to 0 is 0 for x less than 0. So this function is a very interesting function. This function you will see or might already know is called as ReLU function. So this particular function is continuous over entire R, and then this function f obviously belongs to this function fx obviously belongs to f. However, the step function does not belong to x. So what is the step function? The step function gx is basically this function. So for x, so this is the graph of the step function. So how do I define step function? So fx is equal to minus 1 for x less equal to 0 is equal to 1 for x greater than equal to 0. Then clearly there is a jump in the graph. The function is not continuous at x is equal to 0. So gx does not belongs to f. Gx does not belongs to f. And how do I define addition of two functions? Addition of two functions is straightforward. So how is the addition defined? So addition is defined in this particular way. fx plus gx is actually equal to f plus g evaluated at x. So that's how the addition of the two functions is defined. And alpha f of x, alpha f into x, that is how scalar multiplication is defined. And with this definition of addition and scalar multiplication, you can show that f is also a vector space. So f is also a real vector space, So saying that it's a real vector space is saying same as f is a vector space over R. Both the things are same. So saying that f is a real vector space, it's same as saying f is a vector space over R. So this is how I define addition and scalar multiplication, and under these two operations the set of all continuous functions becomes a vector space. The fourth example that I want to take is a very interesting example. So what is that example? The example that I want to look at is the following. I define a set B, or I define a set W to be set of all vectors of the type x1 x2 such that x1 plus x2 is equal to 0. This is the set I defined, W to be the set of all ordered pairs x1 x2. So clearly this set is a subset of R2. This set is a subset of R2, and the question we want to ask is W a vector space over R? Is W a vector space over R? So what are the operations? Operations are the same operations. Vector addition, how do you define? Vector addition, component wise. The same way we have defined the addition of vectors. And scalar multiplication, again component wise. So we define scalar multiplication also component wise. So if this is the way we define these two operations, then under these two operations is W a real vector space? So the first thing that I will like to look at is the vector 0. And do you all agree that this vector belongs to W? Obviously this vector belongs to W. And then I think you can very quickly and easily check that all the axioms in the definition of a vector space are satisfied. So the answer is W is a vector space over R. Okay. But an important thing to observe here is that W is a subset of R2. That is something that is really very interesting to observe. R2 in itself is a vector space over R. R2 in itself a vector space over R. So we have a subset of a vector space, and that subset also turns out to be a vector space. Is that special because the vector subset that I am considering is special, or will that happen for every vector subset? So another example, W. So if I call this W, okay, then if I call this set Z to be set of all vectors x1 x2 such that x1 plus x2 is equal to 1. Then is this set vector then is this a vector subspace? Is Z a vector space over R? And the answer is no. Can you tell me why? The very reason is that this vector 0, 0, the 0 vector, it does not belong to Z, because in order that the 0 vector 0, 0 belong to Z, the addition of components should be equal to 1, but here the addition is always going to be 0. So 0 vector does not belong to Z. So if you see the property, the axioms, this particular third axiom of existence of 0, this particular third axiom about existence of 0 is actually violated. It does not, this does not exist, and that's the reason why this particular set is not a vector space. So not every subset of a vector space is a vector space in itself. So it looks like the sets of this type, are spatial. Okay, the sets of this type are spatial, and these spatial subsets, which are vector spaces in themselves, are called as vector subspaces. Okay, vector subspaces. Very, very important vector subspace concept, because this is something that will come back to us when we try to solve system of linear equations. So this is something that is very important. So vector subspace, let us write down the definition of this vector subspace. Let V be a vector space over R. Let W subset of V, then W is called a vector subspace if W is a vector space over R. So if W is a vector space over R in itself, then this is a vector subspace. Okay. So this is something that is really very important, and geometry behind this subspaces is really very nice in R2. Okay. So in R2, R3, Rn, we can see the geometry. So for example, this space is R2, and look at the first example that we looked at. That was x1 plus x2 is equal to 0. So x1 plus x2 is equal to 0 actually is the line. X1 plus x2 is equal to 0 is the line, and that line is this line which passes through origin. So this line is x1 plus x2 is equal to 0. So this basically is W. And what is the other line? The other line is set of all points x1 plus x2 is equal to 1. So if x1 plus x2 is equal to 1, then it's the intercept. So it is the line parallel to this line. So this is the line, right? So this is x1 plus x2 is equal to 1, which was nothing but the set Z. So you see, this red line is not a vector subspace. So this is not a subspace. But this line is a subspace. So in fact, geometrically, you see all the lines passing through origin will be subspaces of R2. And why I require lines? I require lines because I am talking of linear space. Okay, I have defined addition. So in order that it's closed under the way I have defined vector addition, I need lines. Okay, so you need to have a set which contains origin in order to have additive identity. So this straight line is ruled out, the red one. But you cannot have any arbitrary set of this type which passes through origin, and this will also not a subspace. And this is not a subspace because it will not be closed under scalar multiplication. It will not be closed under addition. You add two vectors in here, they will not lie in the set itself. But on the green line, that will indeed happen. And that's why the green line is actually the vector subspace. And the other two figures that I have drawn, the red line and the pink curve, they are not the vector subspaces. That is something that is really very important. So you can actually characterize all the subspaces in R2, geometrically. How do you do that? So singleton 0 is trivial subspace, R2 itself is another trivial subspace, and any line passing through origin, that will also be a subspace of R2. That is something that is really very important. So geometrically, this will characterize all the subspaces of R2, and you can do the same thing for R3. So if you want to characterize all the subspaces of R3, so the 0 set obviously will be, but you have to remember this 0 is a vector in R2, so it has two components 0, 0. This vector that I have written down, so this vector is a vector in R3. It has three components 0, 0, 0. Okay, so that's R3 another. Then any line passing through origin and not only that, any plane passing through origin. So you think about it. So these are all subspaces. These are all subspaces of R3, and these are all subspaces of R2. And you can take this analogy forward to Rn and tell what are all possible subspaces of Rn geometrically. So that is something that is really very important, and this geometry is really very important to understand. You think about it. If you don't understand, please make sure that this doubt is cleared at this very point, because the whole least squares and the whole system of linear equations will be based on understanding of these subspaces of Rn. So if you do not understand these subspaces of Rn the way we are going to develop the theory of least squares, you will not understand the proofs of least squares. So please make sure that you understand this concept thoroughly. So once we have done these concepts of vector spaces and vector subspaces, let's go back to our examples of Rn. Okay. So back to the example of Rn. So in Rn, we already have seen two operations, vector addition and scalar multiplication, which make this Rn into a vector space over R. We want to define one more operation on Rn, the vectors of Rn, and that operation is called as inner product. The operation is called as inner product. Okay. So how do I define inner product? So for any two vectors x and y, for any two vectors x and y in Rn, x transpose y is defined as summation xi yi, I going from 1 to n, which is nothing but x1 y1 plus x2 y2 plus xn yn, where what are these xi's in the notation that we defined in first class? X is x1 up to xn and y is equal to y1 up to yn. These are the vectors that we are looking at, and x transpose y is defined in this way. Okay, this is called as inner product. And what are the properties of this inner product? So this is something that is really very important. So this inner product actually is going to help us to define the concept, which is a very central concept in linear algebra, of distance or the magnitude of a vector. And this distance or magnitude of a vector is going to play a very, very crucial role in many AI and ML applications. How do you define this distance between the vectors? So this distance concept will give rise to similarity. Okay, which two vectors you call same or similar? And once you have this concept of similarity, you can start doing discrimination, which will give rise to the concepts of k-means clustering or different types of similarities, and then they will give rise to clustering algorithms basically. So that's why this concept of inner product is really very important. So what are the properties of inner product? So the properties of inner product, so the first property is x transpose y is same as y transpose x for every x and y in Rn. So this is like commutativity. The second property is alpha A transpose B is alpha A transpose B for AB in Rn and alpha is in R. So I hope you understand what this operation is. So basically this again is kind of associativity, and this associativity actually helps us to do operations in any way whatsoever we want to like. Bracketing is not really important. That's the message that we are getting here. And the third one is distribution. So what is the distribution? Distribution is A plus B transpose C is A transpose C plus B transpose C. So A plus B transpose C. So this is how the inner product distributes over addition. Okay, inner product distributes over vector addition. So that's the property. So these are the three important properties. These are the three important properties of inner product. And using these three properties, you can derive something which is again a very important thing. X plus y transpose A plus B is X transpose A plus X transpose B plus Y transpose A plus Y transpose B. So you can write this down, expand it in this particular fashion, and this is very useful stuff. Okay, so now examples. Okay, some interesting examples about inner product. So the first example about inner product is inner product with unit vectors. Okay, inner product with unit vectors. So what do we do? Let EI be a ith unit vector in Rn. Then for every x in Rn, you can define EI transpose x, and this EI transpose x will be xi, the ith coordinate of x. So you do inner product with respect to ith unit vector, you get ith coordinate. So very straightforward but interesting thing. The second inner product is sum. So you consider the vector of ones in Rn, and if I take for every x in Rn, if I do this, then this is nothing but summation xi I from 1 to n, the sum of all coordinates of x. So this is something that is really very interesting. So if you have data point x and you want to sum all the data points, this is the inner product operation you do. Once you understand this, then you have something which is called as average. So for average, what do? You take inner product divided by n. So let me write it properly. So 1 transpose x, which is nothing but summation xi divided by n, I going from 1 to n, which is nothing but average of x, the vector x. So this average is little different than the average that we looked at last time, the linear combination average. So there we were looking at the average or the mean of the vectors. But here what we are doing, here we are looking at the average in the entries of the vectors. So average of entries of the vectors. So this is the formula, and that average can be obtained as inner product. Then sum of squares. So what do? For every x in Rn, I can define x transpose x, which is nothing but x1 square plus x2 square plus xn square. So this is sum of squares. Okay, so this is again extremely important example of inner product. This forms the basis of the loss function that we define in regression. So this sum of squares is extremely important. Also gives you a sense of distance. So this inner product will also give you sense of distance. So this is extremely important example. And we had done something about block vectors. So let's define block vector inner product. So this block vector inner product, so suppose x is x1, x2, xn blocks, and y is equal to y1, y2, yn again blocks, such that x1, y1 belonging to Rn1, that's the length n1, x2, y2 belonging to Rn2, and so on and so forth. So here I use n. So xm, ym belonging to Rnm. Then x transpose y, the inner product between these two, x transpose y, inner product between these two vectors will actually be x1 transpose y1 plus x2 transpose y2 plus so on and so forth, xm transpose ym. So that's how you will define the inner product of the block vectors. So, so this is something really useful. And once we are in place with all these block vector inner product and so on and so forth, what are the applications? What are the applications of inner product? So let's look at these applications. Okay. So the first application of inner product, you can take it as co-occurrence. Okay, so what is co-occurrence? Co-occurrence is there are, say for example, 10 objects. So there are 10 objects and 2 sets. 10 objects and 2 sets. So both the sets may not have all the 10 objects. One set has say 7 objects, the other set has 5 objects. So if an object is present, then I say 1, if object is absent, then I say 0. Then I can construct two vectors x and y corresponding to set 1 and set 2. And x and y, these are the vectors of ones and zeros, one indicating that object 1 is in set 1, object 2 is in set 2, and so on and so forth. So these are all vectors x and y in R10. In fact, x and y are vectors of zeros and ones. So what will x transpose y tell? X transpose y will actually be number of common objects in both the sets this is straightforward. So x transpose y is actually telling you the number of present in the intersection co-occurrence occur in both the sets, right? So that is something that is important. The second application is weights features. Okay, weights and features. So what happens here? So suppose let x be the feature vector, okay, feature vector, and let y be the weight vector or scores vector. Then what does y transpose x represent? That's the question we are asking. So for example, in an example where you are a banker who wants to give loan, okay, and let x be the feature vector. So it's a feature vector associated with a customer. So what are the features? The features are age, salary, previous loans, and things like that, right? So these are the features. So age might be 50, salary might be 50,000 a month, and so on and so forth. And y is the weight vector. So you have a rule for weights. You have a rule saying that if age is more than 40, the person is less likely to repay the loan, so don't give loan. So the score is less. If the person is 30 years old, then he or she is highly likely to repay the loan. So the score, the weight corresponding to that feature is higher. So that's your weight vector. So what will y transpose x give? The y transpose x in that case will give you credit score. It will give you credit score, and based on that credit score, as a banker you can decide whether you want to give a loan to this person or not. So inner product. So this type of inner product of weights and features always come into the picture. They always are of central importance to us in many AI and ML algorithms. So that's why this type of inner product is once again a very important inner product. The third example is something that anybody who took PropStat course from me would have learned from me, right? So what is the vector? So vector P is probability mass function, okay? So this vector P is a probability mass function, and vector X is actually the values of quantities at the EMF points. Then what is X transpose P? This X transpose P is nothing but expectation of quantity, right? So that's how you define expectation. So let's take one example. Through that example it will be clear. So let P be the PMF. So P, let P be 1 by 6, 1 by 6, 1 by 6, 1 by 6, 4, 5 and 6, right? So this is a vector in R6. So what is the random experiment? The random experiment is actually throwing a fair die and the probability equiprobable. So equiprobable space is considered. So each face is equally likely to come on top. So 1, 2, 3, 4, 5, 6 with probability 1 by 6, 1 by 6, 1 by 6. So this is a PMF. And what is X? So the quantity, I will take that quantity as random variable. So the values that I observe on the face. Okay, I will just look at that. So what is X transpose P then? X transpose P is 1 into 1 by 6 plus 2 into 1 by 6 plus 3 into 1 by 6, 4 into 1 by 6, 5 into 1 by 6 plus 6 into 1 by 6. That's nothing but the expected value of this random variable X. So what is the question I am asking? The question I am asking is, what is the expected value? What is that value on an average that I will see when I throw a die? So this is the expected value. This is the average value that I will see. So 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6. So that's the expectation of this random variable, right? So this expectation is nothing but the inner product. Another important application is polynomial evaluation. Okay, polynomial evaluation. So this polynomial evaluation is a very important tool again in regression problem when we do polynomial regression. So there also this thing comes into the picture. So suppose for example Px is a polynomial given to us, which is given by P0 plus P1x plus P2x square plus Pn x to the power n, right? So this is a polynomial of degree n. Then I can form the vector P from the coefficients P0, P1 up to Pn, and I want to evaluate Px at x is equal to x0. If I want to do that, then I construct the vector. Okay, so I chose a bad notation by using a. So suppose I construct the vector, which is nothing but 1 x0 square x0 to the power n, right? So this is the vector. Let us call this vector E. Then what is E transpose P? E transpose P is P0 plus P1 x0 plus P2 x0 square plus Pn x0 n square, which is nothing but this polynomial Px evaluated at x is equal to x0, right? So inner product is polynomial evaluation. So this is something that is really very useful in polynomial regression problems. So these are the few examples. These are the few examples of applications of inner product. And before closing this lecture, I want to say something about complexity. So this is something that you might have looked at in some form or the other. So what is complexity? So the complexity is roughly the number of operations like additions and multiplications that I do. For me, as far as this course is concerned, this is what I mean by complexity. Otherwise, complexity has a huge meaning. It can be a spatial complexity problem where you are thinking of the space required to store one particular object, or computational complexity, which is what we really are talking of. The computations, how many number of operations are required, and then there is time complexity. So in 1 second, how many number of operations like addition, multiplication, comparison a computer can do, and based on that, how much time will be required for that computer to perform these many number of operations. So we will not look at all these three different distinctions. We will only look at the complexity in terms of number of operations, which are nothing but additions and multiplication. So if you have two vectors x and y, if x and y are two vectors which are in Rn, then in order to perform x plus y, how many number of operations are required? So x plus y is indeed x1 plus y1, x2 plus y2 and xn plus yn, right? So there are only n operations. What are those n operations? N additions basically, correct? So n additions are required. Similarly, for inner product alpha x, you have alpha x1 up to alpha xn. So again you have n operations, but those n operations are now multiplications, right? You have to perform n multiplication operations. So alpha x is n multiplication operations. And the third thing that we studied was inner product x transpose y, which is nothing but x1 y1 plus x2 y2 plus xn yn. So here you are required to do n multiplications, and how many number of additions? N minus 1 number of additions. So total number of operations is 2n minus 1. N multiplications and n minus 1 number of additions. So total operations 2n minus 1. So so this may not seem very significant at this point of time, that how many number of operations or complexity is required, but as we go further and we start doing more complicated operations, we will realize that this really comes into the picture. So in summary, what we have done today, definition of vector spaces and subspaces, subspaces, examples, inner product, examples, applications, and concept of computational complexity. So these are the things that we have covered today's lecture. Next class onwards, we'll start doing some interesting things like linear functions.